welcome back. The topic now is deep frying. It looks like it's nice to see that the room is completely full. It's nice because this room I think is the hardest to find, fifth room Theta. So without no further ado, we are going to begin with Glenn Henriksen. He is a mentor and developer from Norway. He's the co-founder and CTO of Justify. He has been a Microsoft development MVP, and in the past 20 years he has co-owned 2 companies, worked as a consultant, manager, support tech, network admin, developer, architect, technical lead, and more. So he's going to tell a few words about himself, I guess. Building that glorious monolith and carving it too. So let's welcome Glenn on stage.
Thank you. Yeah. To be clear, I told him you could read all that online, but... So I'm Glenn. I'm glad so many people found this backwater hole of a room. I had to go looking for it this morning. It's like, where is my room? So, just because I'm curious, how many of you are currently working with distributed services or microservices or whatever definition you see? Okay. How many of you feel you should be working with microservices? How many are not but kind of want to? A couple. How many are working with microservices that feel like we shouldn't really have done that? There's a couple of those as well. Okay, cool. Who's working with the monolith? Okay. I haven't defined monolith yet, so everyone has their own definition, but that's cool. We'll get to that. It's a safe space we can share. Who's working with a distributed monolith? There's a couple of those as well. Okay. Just to level set. So yes, I'm Glenn. I work at a company called Justify. We're a startup getting into scale up, and I'm going to talk a little bit about how to not do microservices, because that was a benefit for us, and I think that's a benefit for other people. So a monolith. It doesn't sound good. The word hasn't got a lot of positive connotations. If we define it, it is a large single upright block of stone, especially one shaped into or serving as a pillar or monument. No, I'm still not getting that good warm feeling. Let's try another definition. Large impersonal political, corporate, or social structure regarded as indivisible and slow to change. Nah, I'm not feeling it. Doesn't sound fun. And then you have microservices, and people talk about these things. Architectural style. It sounds cool so far. It's structures, applications, collection of services that all together are highly maintainable and testable. They're loosely coupled, independently deployable, organized around business capabilities, and they're owned by a small team. And this all sounds good, right? And this is what we're often not necessarily taught, but this is a story we read. All the advantages of microservices. And we get this impression, all of these are good things, to be clear. All of these are good things. And we get this impression that monoliths are bad and microservices are good. And we get that when reading blogs and everything. And as technologists, we often have, I'd say, a fetish for shiny things that seem a bit challenging, that tickles our brains. And so we go into those things. But distributed computing, as you do with microservice, we take an app and we split it into multiple pieces, multiple apps, and run them separately. That's microservices. And the services are small. They have a very defined purpose. This service does this thing. This service does this thing. And the trick with microservices is finding that scale. How small, how big do they have to be? But there are some fallacies that people don't think about with distributed computing. For instance, that the network is always reliable. They just assume that. How many times do you call a network service without any logic for timeouts, retries, what happens if the network is down, if it's slow, whatever? People do that all the time. We just assume that the network is always there. We assume that the latency is 0. Sure, we can split this business process across 45 different machines. It'll be just as fast as if they're running in the same process, because the network doesn't add time. We assume that bandwidth is infinite. that it doesn't matter how much stuff we put between two machines, it'll just work. We assume that the network is secure. We don't have to worry about that thing. The topology of the network doesn't change. It's always the same. This service is always available here, always available to that name. There is one single person you can go to for everything to administer this. There's no fighting among who owns the firewall and who owns the server, and you have to talk to this guy to fix this one, you have to talk to her to fix this, and you have to talk to him to fix the other thing. We just assume that doesn't happen. There is one contact point. Transport cost is 0. I know a guy that works with reducing bills in AWS. One of his biggest points is reducing network traffic. Because depending on what you do, you can pay quite a lot of money for internal network traffic in Amazon. And we assume that network is homogeneous, that it's always, everything's the same, right? There's no differences there. All of these things you have to handle when going down the microservice path, and these are the stories they don't tell you. But the other alternative that's presented doesn't seem that attractive either. Has anyone heard of the term big ball of mud? It's a technical term used to describe monoliths as a big ball of mud, the spaghetti code, right? These monoliths, they are limited in their architecture. They have limitations in size and complexity. You can only grow them this far, a big ball of mud, because it becomes unwieldy. A big ball of mud is too large to fully understand. You can't look at it and grasp the entirety of what is going on. These are common problems with these balls of muds. I'm sorry, I forgot to turn off the audio on my timer here. The application size slows down the startup. It takes a long time to start. It has to do a lot of things. You have to deploy the entire application for every single update, which might or might not be a problem. And some of the most important ones, when you have a big ball of mud with full of spaghetti code, the impact of a single change can be really hard to see what's going on. So you get this fear of changes. And it becomes a barrier to adopting new technology because you can't necessarily introduce something new into the monolith without touching all the other parts. And so we felt these. Now, most of these problems can be overcome using various techniques, and we're going to look at those things. The main problem here is that when something grows, something becomes bigger. There are almost laws of nature that says that complexity will grow as well. Because if you have two things and they talk to each other and you introduce a third thing, the number of connections increases, because now 3 things have to talk to each other. And these connections increase exponentially. They don't increase linearly. So you add a 4th thing, you get 3 new connections. You add a 5th thing, you get multiple connections, multiples, because everything has to talk to everything. What we have to do is to introduce complexity dampening measures to keep the complexity from growing. The main reasons for the problems in Monolith is that the different parts are usually not very well organized. They're not clearly defined, the lines are blurry, we get an unmanageable amount of coupling. Coupling is the term for how many connections or how connected are 2 parts of our system. There's a phenomenon called the Norwegian arm, since I'm from Norway. Norwegians are known as people that we're not necessarily good at talking to people. We don't like that. We don't like to intrude. And if you ever had dinner with a Norwegian, you'd probably have noticed that they tend to reach a lot on the table for stuff. Because in Norway, it's not right, but in Norway, there's a general feeling that it's more impolite to intrude on the other person in whatever they're doing, to ask them to pass something, than just get it yourself. We're very practical people. And of course, back in the Viking days, we just took what we wanted anyway, so maybe it's from that. But there's a concept of the Norwegian arm on the dinner tables, like, I'm just going to grab the salsa over there, thank you. And the cheese for the tacos. And sometimes you get a Norwegian arm going straight across someone's face. That's highly impolite, but it happens. And so we have the Norwegian arm in software, where one area of application will reach into another area of another application, just grab whatever it wants. So what we can do, we can make smaller and more contained boxes. Let's call them boxes. And we limit how they talk to other boxes, how they are connected. So this helps with a lot of problems, provided we are reasonably smart when creating these boxes. We should be able to build boxes that are small enough to fully understand, small enough to not have a lot of complexity, and small enough to understand the impact of a change within a box. Now we want to keep coupling as low as possible. There's a measurement in our code. It can actually be measured by various analyzers. There's another measurement we want to control as well, which is cohesion. Things that belong together should be together. That is a number we want high. It's harder to measure because it's more of a discipline and a thing we know that things that belong together should be together. We shouldn't have to go hunting all across the app to find things that are about the same thing. So and we can organize these boxes in folders. So we can have a bunch of boxes as a folders, and we collect functionality within one of these folders. And within a folder, we have a box. Okay. Let's do a fast track. Actually, we can do this because I know PowerPoint. Here we go. Don't press the escape button again. Now, your box should have a clear boundary. It should be clear on what it communicates with other boxes and what is the internal stuff. Inside our box, we have two layers. We have the domain layer, let's call it domain, which is the domain, the thing that the box is about, right? We call that the domain. Anyone familiar with the term domain? Yeah. So that is the thing that the box is about. It could be users, it could be identity, it could be forms, it could be search, it could be whatever. But it should be self-contained. You should be able to look at that domain and reason about it in a way that makes sense without involving a bunch of other domains. And then we have an application layer on the outside. The domain layer is completely internal to our box. Nothing from the domain layer should escape outside the boundary of our box. We should not have a Norwegian arm reaching into the domain and grabbing stuff and pulling it out. Inside your domain, you have your business entities, your aggregate roots if you have those, your value objects, your domain services. Any changes in here are for business purposes. The application layer interacts with infrastructure. It decides how stuff goes into the domain. Maybe it communicates with the database, pulls stuff in, hydrates a bunch of domain objects. And it decides how can other things communicate with our domain. Carry on my way. So here we have, outside the domain, we don't have our business entities, but we have DTOs, data transfer objects, specialized objects used to just transfer data. Our domain objects, they have behavior, they have logic, they have methods. All the logic is contained in here. And any tests we run on these objects will run business tests. Services and objects in the application layer, other boxes can have a dependency on those. So inside our domain, we have a thing. This domain object has behavior, has logic, it has data. It has functions. There's business stuff into it. And we can have a thing service. The thing service returns a thing DTO, data transfer object. The DTO is simply a data object. It has no behavior, no functions. It's just a pile of data to be shipped off somewhere else. If someone says, hey, I need information about our things, they will call our thing service and they will get a list of thing DTOs back. So we have this insulating layer between our domain and everyone else. This enables us to loosely couple these domains. I can now make changes in my domain without necessarily touching the outside of my box. So if my business logic changes, I can change my thing, and I can in many cases not have to touch the thing DTO at all. Controlling the surface of our boxes is one of the things that make it easier to manage the complexity because the couplings are more static. Using principles from domain-driven design, anyone familiar with that? Yeah, a few. If not, you should look into it. It's a really good way of designing applications, at least complex, non-trivial applications. But you could use principles from domain-driven design like bounded context, domains, subdomains, and organize these boxes, helping to keep things understandable. One such box is self-contained with all its logic, all its data. You can reason about the domain in such a box in isolation. You do not need to understand all the other boxes in order to understand this one and do work here. Which makes it a lot easier for new developers to come in and work on something, because you don't have to explain the whole monolith to them. You explain this box. And you say, in this box, I want these things to happen when so-and-so happens. Now, boxes is a really poor name. In our application, we call them features. It's an arbitrary name. Pick a name that makes sense to you and your team. Context, domains, whatever. It's not really important as long as it makes sense. I'll be calling them features from here on out. Now, the communication border, you should treat that as a public API. You should be very aware of changing it. But again, in a monolith, there's where you get some of the advantages of a monolith. Because changes, wide-reaching changes, are much, much easier in a monolith than a distributed application. Because you usually have an IDE that will help you refactor. Refactoring in an IDE where they have the whole application loaded is pretty easy. You F2, rename a variable, rename a property, rename a class, boom, it works everywhere. Seeing what things will change is easier. References, here are all the places where this object is referenced. Great. Now we can see what happens. I can much easier see the impact of my change. Even if I don't have tests, which I should, but even if I don't, before I run all the tests, before I make the change, it is much easier than Monolith to get an overview of the impact of changing this. And since I've isolated, I know that anything in here, I can change whatever I want without impacting anything else, as long as I keep my public surface clear. Any external dependencies is also handled from the application layer, usually insulated from your domain code through a service or a thing that will talk to an external service and translate things into my internal domain language. Domain-driven design, call these an anti-corruption layer. But it's a piece of code that prevents concerns from external features. They can be other features in the same app. They can be external services anywhere to influence and drive changes to my domain. So if my thing wants access to a Bob, I have a service here that will talk to the Bob domain and get information and then use that information in the logic it has. Now when starting out, you might be tempted, or it might make sense to have a thing service and say that everyone who wants a thing or something from the thing domain, you go through the thing service. And that's fine in the beginning, but it gets weary and it gets old really fast. Because you have the thing DTOs, and you have multiple stuff, multiple things that want stuff from the thing service. You have multiple endpoints if it's a web application, or screens if it's a desktop application. And so that makes it really hard to make a good containable thing service. What we do, we like to split it up in various use cases. So we have various use cases saying, hey, if you want to do this, then we go here. If you want to do this, you go here. And we have multiple types of DTOs. A DTO for showing the details of something is not the same DTO as showing a list of something. And we can have multiple thing DTOs, and we can have other things in the domain and stuff like that. And having a single thing service along with multiple thing DTOs, probably not the best cohesion we could have. So we like to split this up. We have different ways of splitting it up within inside a domain. We use different folders to organize different features. And what we do is that we split it up in command requests. We're going to zoom in on this. Don't worry if you can't read it yet. You're not supposed to. We have various request command handlers along with specialized requests or commands and sometimes responses. One for each use case in our feature, or each user story often. We group these in a single file under a namespace or a class definition, nested classes. I like using nested classes because it makes me use the class name, the main class name, and I can have common names inside. I can have the query, response, handler. It's mostly a stylistic choice, but it does remove some of the need of discipline. So here I have a class getMyVault. So in our application, we have a feature called Vault, where a place where different documents are loaded or stored. So I have a getMyVault. That is the use case. I want to get my particular vault. I have a request, a query class, and I have a handler. And this handler returns a Vault DTO class. We're using Mediator, a framework that allows us to create and just send requests without worrying about where it's picked up. It fits very well with this model. This model suits us very well, making it easy to create small handlers, associated requests, associated response classes. We usually have DTOs acting as response classes, but we can make custom ones in custom cases. The thing what we don't do is that we don't return the domain objects. We never return domain objects from our handlers, always DTOs. Mediator also allows us to stuff together. Here we have the record query. It has a property, Vault user ID. It has an interface on top here, I require registered Vault user. It's a marker interface, and Mediator lets us attach behaviors. And we have a behavior saying any request that is marked with the I require register Vault user, a small behavior will run before the handler that will populate that Vault user ID field. So that I know in my handler, I know that that is taken care of. So down in my handler, and this is all the code for the handler, I know that I have a Vault user ID. And this is pretty easy to reason about, especially if you know a little bit of how the Vault works. You can look at this handler and say, okay, that's what's happening here. Very easy to reason about. This is all of it. There's a bunch of infrastructure taken care of outside of this in behaviors. We have auditing, we have logging, we have populating IDs. These are infrastructure that we just attach and they just work everywhere. The whole file fits on the screen, at least most screens, and with a readable font. Very easy to reason about each individual use case, and it has no dependencies to other use cases. This is not a lot of code, and we have a bunch of use cases. This code can easily fit in your head. You can look at these and say, okay, I want this thing. Go in, see what it is. We have reasonably descriptive names, easy to find. When a feature needs some other information. We also use services internally because calling features from handlers and mediators is not really supported, and it makes weird things if you have behaviors. But these service classes will usually be limited in size, and if not, we split them up. We have a bunch of services that do specific things, and we use them, we inject them into handlers, or we inject them into other features that want to use stuff from our service, our domain. We can even take our API endpoints. These are endpoints for the web server. We can put this in one file. Here we have a file, add task endpoints, an extension method to web application. And we just add the different endpoints, and we use mediator send, new update request, mediator send, create request, mediator send, get list request. So the handlers, the endpoints here for the web server are pretty slow. We can put that in one file, and we can just do add task endpoints. So we can take all the stuff that belongs in that feature and move it into that feature folder. High cohesion. And now you're thinking we're treating our little feature sort of like a microservice, and you're entirely correct. We are. We are enforcing some of the constraints that you have with microservices onto parts of a monolith. So we kind of pretend we're making microservices, but we're not. But we take some of the constraints that make sense and put them on top of this. And one of the constraints in a microservice is that a microservice should be self-contained, including its data. They are autonomous. So how do we do this with our features? Well, should every feature has its own database? We think that's a bit excessive. It could have, it doesn't need to. What we do, the important thing is that our features owns and controls its own data. One of the problems with monoliths is that that people run into is that they have features and they start integrating features in the database, which is a bad idea. Because then you have concerns in one feature through the database affecting another feature. So you don't want that. So one feature has its own set of data. In most databases, you can use what's called a schema as a namespacing functionality. So there's a difference between a vault user table and a chat user table. Vault and chat are schemas in our database. They act like namespace does in C# or Java. So we have separate user tables that have separate data, separate structure. They don't interact at all. We can even set permissions, saying that one connection string only has access to anything beginning with vault, and one connection string only has access to chat. We use entity framework, and in our DB context, which is the class that is, anyone use entity framework here? Yeah, a few. So entity framework is an ORM, object relational mapper for .NET, which will connect the domain objects to our database. So we can say stuff like, get me all users that satisfy a concern, and it will do the job of going to the database, translating my request to SQL, going to the database, getting these objects or data, hydrating my objects, and giving me objects back. It uses the database context as its unit of work, or its repository. And what we can do here is that we can set a schema. And we can say that when we build this model, it has a default schema. And we use an abstract class with an abstract string of schema, forcing me to override that in any any child implementation, helping me fall into the pit of success. So we have a separate DB context for each feature. We have a vault context, we have a chat context, we have a this context, we have a that context, and they all inherit from a base class. Removing a need for discipline using abstract classes and stuff we're used to. Now, some of you are thinking, oh, well, aren't we duplicating a lot of data? We have several uses objects. Yes, we do. Because in the vault, we have the concept of users, but they're different from the concept of users in the chat. And they evolve differently. In the Vault, we have users that have registered with us. We have some unregistered users. How do these translate to each other? How does this work with a registered user comes in and all kinds of stuff. I won't go into the details, but they're different. A chat user is a lot different from a logged in user, an identity for a user, which is a separate thing again. And so yeah, we have separate purposes, separate objects. Identity domain or feature has one user, Vault has one user, a Forms has a user, a chat has a user. How do we keep these in sync? We usually use events. So we want a change in one feature to have an effect in another feature. If a customer changes their name, we want that name to be updated in the chat and in the form context or features. We don't care about Vault because we don't carry the name there necessarily. So we use events. Again, the advantage of having a monolith is that you can use in-process events. You can have stuff happening and register, hey, this thing just happened. And then we use Mediator, which works well for this. You can fire off, publish an event, and we have handlers for events. So in our identity context, if the name of a user changes, it fires off a username changed event, which is picked up by our chat, has a handler for user changing the name, which changes the name of the user there, and the chat or whatever other feature that might need you have a user. The form, that's one. A form will pick up the name there. There's many ways of doing this as well. We use a technique that Steve Ardalis has a clean architecture where we have an entity base class for all entities, where we have a collection called domain events. And whenever something interesting happens in one of our domain entities, we add an event to this collection. So these are decided inside the domain. Hey, here's some interesting fact that happened because we have functions, we have behaviors. We don't just set data. We call a function saying, change customer name. And that creates an event saying, hey, this thing just happened. It's put in the domain events collection. And what we do in the DB context, we override the save as method. So when we save entities, we also see, are there any domain events that need to be published? So we pick those up and then we publish them. They're handled, and we have ways of doing this since everything's going as the same database, even if it's different schemas, we have transactional integrity. So that works out well for us. Now, working on a monolith does require a bit of discipline. We have a clearly defined features, we have the domain objects, application level services, handlers, own corner of our database, external communication is handled, we have an installation layer there, we have request command classes, everything is working fine. But what is stopping our developers from just doing the Norwegian armor and reaching in somewhere? Nothing. Really. After all, everything is in the same application. Nothing is further away than a simple using statement. So there is, in essence, 3 ways you can prevent this. 1, you trust your developers. You say, well, our team consists of mostly functioning adults. So we decided in collaboration that this is the way we do it, and we expect people to follow this. And people screw up, sure, they do, but we have code reviews, we have pair programming, we have mob programming. We work in ways that prevent a single person from making a mistake that blows everything up. We can create separate projects for our features. And we use language or project system features to ensure that these things can't talk to other. This feature can't talk to that feature because they don't have a reference to that project. But they need to talk to the application. So we have an application project, and then we have separate domain projects, and we have to have separate application projects. And I think that becomes a huge mess pretty fast. I'm not a big fan. I like alternative one because I usually work with functioning adults. There's also ways of using enforceable rules in your code with static analysis. There's code analyzer. For instance, in .NET, there's a project called NSDepCop, where you can set rules of what namespaces are allowed to communicate with other namespaces. And it will give compiler errors for any violations. So we can say that, and we can make wildcard rules saying that the only thing that is allowed to talk to the vault.domain is the vault.application namespace. But anything can talk to the vault.application. Okay. So then we can say, then we get compile errors if someone doing the Norwegian Army reaching into our vault domain and saying, hey, this thing here from over chat application, you're not allowed to talk to vault.domain. So I like number one, especially if you have a significant degree of trust in the team. The cognitive load isn't that big. Depending on the experience and the way your team works, number three removes a bunch of that need for that discipline. It makes it a little bit overhead in maintaining the rules, but it makes it a lot easier to file new people into the project that may or may not have the degree of discipline you want. So whatever works in your situation, it's fine. So why are we doing this? Why are we making things more complex than they need to be? Well, because it's not really that complex. Sure, we are introducing a little bit more complexity in our monolith than we have to make something work. But we've decided that we don't want things just to work. We want it to work reasonably well, and we want to build something that can grow with us. And so we are taking these principles, some of these advantages, what we listed with microservices, and we're applying those to our monolith. And in return, we're getting an application that is modular. Each modular feature has a clear responsibility. It has a relatively small size. It's being easy to reason about and to think about, and has few reasons for change. The thing we have to add is some discipline. We have to add a little bit of explicit communication. We have to keep that in mind. How do we communicate between features? And we have to think about actually creating features. So when you're making something, you say, okay, what is a feature and what is not a feature? What is a sub-feature? Where do the boundaries go? That's often the hardest part. The things we get back is that we have an application. So starting off, if you say starting off a fresh new application, you're building something new. Starting off with microservices is like downloading a new game. You've never played it before, and you decide to play it on hard mode right out of the box. So starting creating the app with microservices and all that entails, that's deciding to play this game on hard mode. Instead of starting with easy and then getting to know how the game works. What is our domain? How does it look? What are the features? We're in a monolith. Change can be pretty easy. It can be very fluid. It's easy to make massive changes. Oh, this goes over here. This is not really a feature. This goes in here. Much harder if you started with a distributed thing. And once things start to set, you might see, okay, there's some good things about microservices. So what are good reasons for moving to microservices? I've been bashing microservices, but it's not the end of the world. There are legitimate good reasons why you might want to have microservices in your application. Team topology is one. As an organization scales, a monolith doesn't really scale well with the organization. Splitting out parts of your system into separate things, separate applications, to be managed completely by autonomous teams, that can be a really good way to scale. Saying, okay, we're growing, we're getting more and more developers, we're starting to walk in each other's fellow beds, we're over here. We're going to take this part of the application, we're going to move that out, and you four are now responsible for this thing. This is yours, you own it, do whatever you want with it. There can be technical considerations. Parts of the application might have different technical demands than others. We had issues we run on Azure Web Apps, or ran on Azure Web Apps, still do. And we had issues with custom fonts, which didn't work in Azure Web Apps. So maybe a different language is better suited for one part. There's plenty of things that can interact and say, hey, we have technical considerations for this particular domain that we can't squeeze into our monolith. We want to do different things here. Okay, let's take it out. Scale might be one. Your application might be growing, but it's not growing. The needs for performance is not the same across your application. So one part might have a much higher need for scalability than the rest of the application. And it might be cheaper to take that out and scale that part independently than to scale your whole monolith. So you want to build a microservice. Do you want to build a microservice? So the thing about building a distributed application is that if you're not careful, you're building a distributed monolith. We have all the disadvantages of the big ball of mud added on top of all the disadvantages of what distributed computing. But if you've been paying attention to what I've been saying and created the app in the way we've been talking, it's relatively easy to take a part of your monolith and carve it out of your application. Because everything in a domain, in a feature, is self-contained. So we can almost take that code, copy it, file new project, copy the code in. We need to hook up some infrastructure in the application startup, which is mostly a copy-paste job. But it should run pretty much out of the box. And we've done that. It's a matter of, here's a feature, here's all the things in the feature, shove it over there. The only part that is inconvenient or difficult is how do the other boxes, other features now communicate to the one that left? Because it's no longer in process. We can, if the other features communicate through its services, we can easily create a new version of that service that has the same API, but instead of doing calls into the domain, it will now do network calls to the remote endpoints. So all the remaining features will still use the same interface, use a similar service with the same methods, except now they're calling across the network. We have events. So what we need to build the first time we're doing this is we need to build an event structure that will move events out. And if you have events, I forgot to mention that, but if you have events, there's two types of events. We have domain events, they're internal. And then we have integration events, which are meant to be external from the domain or from the feature. Integration events would probably be asynchronous. So you might already have that in place. We have a monolith, we have different features, but when we have integration events, we send them off to an external event broker. We use Azure Event Grid. So we send events off to Azure Event Grid, which passes them back into the same application, but a different part. Because we have a different part that subscribes to these events. The biggest challenge is transactional consistency, saying that any change here should also happen here. If you're doing distributed computing, transactional integrity is really, really hard, but there are lots of excellent ways around this. I highly recommend, if you're into that stuff, to go to Ian Cooper's session tomorrow called At Least Once, which dives in that specific problem of how do you asynchronously communicate between different services in a robust manner. So, to summarize, starting a new application with distributed microservices, that's playing the game on hard mode. You don't want to do that. And it gives you very little return in the foreseeable future, especially if you're starting off with a small team. I mean, I talked to one guy after another talk I gave, and he was starting out like, yeah, I have a team of 40 people starting in 2 months. And we have 1 year to build an application. Okay, then you should spend 2 months doing a lot of architecture work. But usually people don't start with 40 people on one feature. They start with a smaller team, and the monolith makes a lot of sense in a smaller team where we can all work together. And when your team starts to grow and you want to split out, you can often keep people on different features because they don't, if you have a good infrastructure, these are over here and these are over here. We have several developers working on the same app with different things, but we're split in different features, so it works out really well. The deployment is not a problem until you get really large. It requires a little more thinking, a little more discipline than just throwing something off and having everything interact, but that really fast really breaks down, which anyone had a big ball of mud work with know very well. You make clear seams that you can cut along when you want to pull things out. You have clear feature boundaries, and you're very explicit about what you send out and what you take back. Cross-feature communication is handled through services. So you can cut along that seam if you want to carve something out and say, okay, you still use the same service interface, except now it's a remote service instead of an in-process service. The point, and also I specify this, the point is not to build something that is meant to be distributed. This also happens to be the way to make a good, maintainable piece of software. It's just good practice. You don't have to distribute. That's a bonus. The ability to carve out a feature is a bonus, but what it gives you is a good piece of maintainable, solid code. That's the object of the game. The carving part is just free. Any questions you have? Who has any questions for this? Yes. I'll start here, since he had a chocolate.
So you mentioned that it might be hard to define context. Would you mind sharing any tips or help?
So we use techniques from domain-driven design. So we use stuff like, we talk about what are the things going in here. We define the ubiquitous language and all the things you would do in a domain-driven design workshop for finding what are the bounded contexts, which often maps to features, and whatever context you have would be in a feature. We might have multiple contexts in the same feature, but we would never have context that span features. For us, it's a bit of experience game. Like, okay, this thing is a thing, it's a separate thing. So that splits out off into its own. So it's, and we make mistakes, but in a monolith, it's pretty easy to fix these mistakes. One of the advantages is saying, hey, this thing here, that doesn't work. We need to merge these two things because they're not as split as we thought. Yes? So 2 questions. One, performance when the problem with the data being separate and I want related data from another schema. You said the answer is probably data denormalization, and that you're absolutely correct. We denormalize data. So we have a write penalty, and our app, as most apps, have magnitudes of different number of writes versus reads. So the write penalty is negligible. If you have really high amount of writes, then you have what I would call an edge case and a special problem, and you would handle that differently. And there are lots of ways of doing that. For us, we make business application with business rules or consumer application with consumer rules, and the writes are very, very few. And usually the writes are to one domain. So the performance from the user side is very high. What we do have is that we have eventual consistency. Is that when a write happens in one feature, it doesn't automatically happen in every other feature at the same time, which is fine. It doesn't matter. If a user changes their name and then their name in the chat feature is updated 2 seconds later, nobody cares.
I beg to disagree. In some cases, you change something, you reload the page, and then it's not changed.
Yeah, but if I reload the page, I'm in the same domain. I'm in the same feature, so the page belongs to that feature. So I do a change on a page, it happens, the change is instantly in that feature, and it returns a new page, which is in the same feature, and that data is updated right away. And then the change propagates out to other features. The other question, so we don't do reads or joins across features because that would kill performance. The other question was, which is also a problem you have with microservices, but then it's even bigger. The other question was, we have different DTOs, and what prevents a person from taking an existing DTO and reusing that, and that DTO is massive, except using one. You had a specific case for that, where a project where I used to work, where you had a page that suddenly took a long time to load, and that was weird. Because it didn't have that much data on it. So we looked at the SQL analyzer, and it turned out that page did 1,200 SQL queries to load a page of data. I thought, that was odd. And it turned out it was a mixture of 2 things. It was a mixture of, one, someone had used a DTO that was too big and included too many things. And we had an ORM at the time that was eager loaded, and that was lazy loaded, but also automatically loaded fields that you mapped, and we used a mapper to map the data domain object to DTO object. So it would do, basically, it was to fill select boxes with a bunch of lists. So for each of those, it would do a number of queries to fill a bunch of fields that were never used. So we changed into a smaller DTO that was more fitted, and we went from 1,200 SQL statements to a page to like 5. Which was more effective. How do we avoid that? Well, we treat each handler as a separate thing, and we generally do not reuse DTOs. We often have the response objects in the same class as the query, the response, and the handler are at the same, and we do not reuse those things. We have some that are common because we have some features use cases that return the same object but different with different things. But in general, we frown on reusing DTOs, and that's a thing we do out of discipline, and it is caught in our code reviews or pair programming, and that is one of the ways we work. So that's how we prevent it. When we do request objects, we will often not return the domain object in queries. We will tell Entity Framework or ORM to populate the response object directly. So it only get the object it needs from the the columns it needs from the database to populate that specific object. So did that answer your question? There was another one over there. Oh, we're on time. Yeah, so if anyone wants to know more, I'll be outside. And you can look me up online. That's my Twitter handle. Find me there, or any other method that is on the web page.